First of all, good evening. Thank you for attending the next edition of the JavaScript Live Series webinar. So this is part of our live series of webinars here at Amicus Recruitment. And today we're joined by Sean Barry from lead engineer at Vortexa. So he's going to be giving us a really good talk today based around building out JavaScript pipelines. So first of all, Sean, how are you?
Doing well, thanks. Yeah, good.
Glad to hear it. So I'll just let Sean do like a little introduction. Sean will then share his screen and give like a full introduction to what he's going to be doing. So this sort of session is aimed to be as interactive as possible. So myself and Sean will take regular breaks throughout the webinar to allow people to ask questions. If you do have any questions for Sean, please use the Q&A section at the bottom of the screen and we'll get around to everyone's questions. So Sean, over to you.
Great. Well, thanks for the introduction, Jamie. It's my pleasure to be here this evening, and thank you everyone for your time. I'm Sean, and I'm one of the lead engineers at Vortexa. I think I first started building websites about 15 years ago using Dreamweaver. I don't know if any of you guys remember that, but it was lit for teenage me. And I quickly kind of got bored with like the templates and stuff in there and started messing around with HTML and CSS, and that's really where the journey began. But I've been a professional software engineer now for 7 or 8 years. And now, of course, working at Vortexa as part of the application development team. We're the biggest team in the company, and we're all full stack engineers, and we're all working with JavaScript on a daily basis, building like performant Node API and a pretty comprehensive React application, amongst other things. So yeah, that's a bit about me.
Perfect. Brilliant. Well, when you're ready, feel free to share your screen and we can get on with the presentation.
Great. Okay. So if this has worked, you should all see kind of welcome slide. Okay, cool. Let's jump into it. So about Vortexa. Vortexa is a tech startup in the city of London, and we're working in the 2016, which means we've just had our 5th birthday, and we've grown massively. We're now split across 3 different continents with offices in London, Houston, and Singapore. We are an energy intelligence provider, and primarily we track seaborne oil and related products as they travel around the globe. And we leverage the use of machine learning at scale to provide real-time global coverage. So what does it mean when we talk about the Vortexa platform? Well, this encapsulates many things and how we generate and deliver the data to our customers. So to begin with, we're tracking in the region of $2 trillion worth of cargo globally. Our data is coming from a number of different places. We've got real-time sources and stuff that we're ingesting, satellite imagery, port agents, trusted industry partners, and vessel tracking systems. All of this data has to go somewhere, and the result is a core data set that has around 175 billion different data points in it, with around 110 million being added every day. So that's about 1,200 pieces of data per second that we're consuming and processing. We're the largest ingester of signal data in the industry, tracking over 500,000 vessels in real time. So with such a massive data set, our powerful API allows our customers to perform a near infinite combination of queries, so they can slice and dice up our information in whatever manner they require. And this means that they can kind of dig deep into the insight that's important to them. Performance, this is obviously really important to us. 75% of our queries return results in under 100 milliseconds. And I think the top 95th percentile is under 250 milliseconds, so pretty fast. We offer access to our data through a number of different services. We have our API, obviously, our analytics platform, but we also use the AWS Data Exchange, some plugins like a plugin for Microsoft Excel, and we've built some custom outbound services. So when we're dealing with this volume of data and this expectation of performance from our users, there's obviously a scale. Ingesting, processing, and querying this data requires considerable planning. I've just got a pop-up saying my internet connection's unstable, so hopefully you can still hear me.
Everything's fine, don't worry.
Cool. We're also growing really quickly as a company. So we have the challenge of actually how do we grow and scale an engineering team physically and all the kind of problems that come with that as well. We're also thinking about performance all the time and making sure that it's maintained, even when we're processing really heavy queries to our data that could span, multiple years worth of data at the same time. Usability, is really important to us. It's essential that our customers have a frictionless experience, not just when they're consuming from our API, but also when they're using our other platforms too. We could spend a whole evening just talking about like tech stack and languages at Vortexa, but we've picked the right tools for the right job. And in the team that I'm a part of, the application development team, ADT, our primary technology is Node APIs with React apps on the front end. We do everything in TypeScript within our whole real estate. We also dabble a bit with Python, and more recently we've been doing some experiments in Rust, which we're really interested in. Across the company at large, though, we're using Java, Scala, and a bit of Python as well. So this here is just a quick kind of screen grab I took from our application. It's showing our browser-based React application in action. We're displaying a subset of the vessels that we track on a map. These vessels are getting tracked across the world in real time. And this is just an example of a user kind of filtering through the vessels by what product they're carrying, or maybe what destination that they actually originated their journey in this case, Saudi Arabia. None of this has been sped up, by the way. This is all what you would get if you were using the platform for real. And those kind of dotted lines you see on the projected path of the vessel, they're the output of a machine learning model, which is predicting the destination of that vessel. This here is a picture of our flows screen. Seeing vessels on a map and being able to filter through them is really useful, but our customers also need to be able to explore historical flows globally. So this is just showing a user kind of cross-filtering the data by interacting with different parts of the page, picking different origins, picking different destinations, interacting with charts to kind of narrow down the time span that's being queried. And again, this is all being powered by a Node API and a React front end. So now that you have an overview of what we do and how we do it, I want to talk a bit about the reputation that JavaScript has. So there's this kind of reputation that it's a bit weird. It's a bit of a kind of, it's got idiosyncrasies and it's a bit of an easy language. Unfortunately, there's also this kind of reputation of JavaScript engineers as just being seen as being responsible for changing the colors of buttons and web apps. Now, as important as web banners and e-commerce websites are, they aren't the limit of what JavaScript can actually do. I believe JavaScript is capable of much more, and so does our team at Vortexa. And that's why we actually use JavaScript for more than just API and browser work. We actually have complex production pipelines running with JavaScript right now. So what is the reality? Well, yes, the JavaScript syntax is an easy syntax, but this isn't a con, this is definitely a pro. It means it's easier to learn the language, and it helps us kind of understand code that we've never seen before. We've also got the absolutely massive and the really rich ecosystem in NPM, the Node Package Manager. We've got tools like TypeScript. These bring us static typing, helps us to avoid those kind of JavaScript errors like cannot read property undefined. And when we're using JavaScript on the front end and the back end, we avoid the cost of having a context switch, which is kind of traditionally present when you switch between these two roles. And even better, we can actually take advantage of having shared components, shared utilities or helpers, and constants. This also means that we can hire from the same pool of engineers, and these engineers, because they're working on the full stack, they actually have a good understanding of where the data is coming from, what the schema of it is, and ultimately how it's being consumed further down the line. Another kind of great part of JavaScript is the fact that JSON is a first-class citizen in JavaScript. So this gives us seamless manipulation of data. And two of the most important things is definitely Node and V8. So Node, with its asynchronous, event-driven architecture, it allows us to concurrently process incredible amounts of data and requests, and we can really easily both horizontally and vertically scale. On top of that, Node is written in Google's V8, which in turn is written in C++. Both V8 and Node are frequently updated. They've got performance boosters, security patches, and support for kind of the latest JavaScript features. Over time, we've actually noticed that our systems are just speeding up without us even doing anything. And this is just because of the underlying technology that we're using. So it's pretty clear that we are big fans of JavaScript. And I think now is probably a good time to stop for any questions if there are any.
Yeah, absolutely. We've had 2 questions come through. So first question from Pat. He said, do you use any state management tools in React?
Yeah, we do. So we use Redux pretty extensively throughout our application, and it's great. But we've also recently done some experiments with Recoil. Recoil is going to be super exciting. I personally haven't had a huge amount of time to play around with it, but from the kind of brief intro I've had to it, and from what some of my colleagues are saying within the team, it looks like we will be adapting it as soon as it kind of gets out of its beta phase. Just gives us a bit more kind of atomic state management.
Perfect. Enric has also asked, being that easy to mix front end and back end, same context, same types, how do you make sure things are in the right place with the separation of concerns?
So mixing front end and background. Well, I guess if I understand the question correctly, for a start, our code isn't in like a monorepo for kind of the front end and the back end. We've got 2 different repos, 2 very different code bases, and the kind of glue that binds them together are these interfaces that are defined in tools like TypeScript. They allow us to kind of create contracts between the 2 applications so that they're working off the same kind of schema of data, but they are very independent code bases. And the things that are shared between them are things that are kind of just like a function that may be a utility that will like format a timestamp or something, to give a really simple example.
Perfect. A quick compliment as well from Chris Miller. Said the UI looks awesome, which is obviously good to hear. Yuri has asked, so JSON can be unreliable with big numbers. Did you have this kind of problem?
I haven't personally ran into this sort of a problem before. Some of the kind of limitations we have run into with JSON is just having files that have huge amounts of data in them. I know that other teams within the company rely on the Parquet format quite heavily, and we have ingested data in that format before. But yeah, I can't say that I've got experience with like issues with using JSON. And also, thanks for the compliment on the UI. I'll definitely pass that on to the designers, and they'll be super happy with that.
Perfect. We've got one more question, then we can carry on to the next section. So Robert has asked, is your front end consuming a REST API or do you use GraphQL?
Yeah, we're consuming a REST API. GraphQL is really interesting, and I think we've all played around with it, but we're not using it in production currently.
Perfect. One more as well, if you've got time for it, actually, just from Anita. Do you follow TDD? If so, what is the library?
We don't follow TDD, actually. Our kind of ethos towards tests is we try to test like every kind of new utility function we create, and we try to have as sensible a test coverage as possible, but we don't start the process by writing tests and then creating what we need to create to make them pass. I personally have found that quite a restrictive pattern to follow in the past, and I'm glad that it's something that we don't really follow.
Fair enough. No more questions for now, so feel free to carry on, and any more that come through, I'll let you know.
Cool. So you guys have heard we're big fans of JavaScript, but this talk isn't really going to be a deep dive into the actual internals of JavaScript itself. I didn't want to come here tonight and talk about a specific part of the language that most of you already know about, or you could just learn about it by reading documentation. So you're not going to be seeing a ton of different code examples or snippets on the screen this evening. Instead, I want to highlight that actually JavaScript is a language that can be used in a data engineering context to build serious production systems handling large amounts of data. And hopefully along the way, 1 or 2 of you will learn a thing. And even better, hopefully some of you will get inspired to push the boundaries and ditch the web banners and do it with JavaScript. So what is the challenge? We recently built an ETL pipeline. So that's an extract, a transform, and a load pipeline within our team. What I'm going to be talking about is why we built that pipeline, how we designed it, what it ended up looking like, and most importantly, some of the lessons we learned from building it. And the challenge that we had is within Vortexa, we've got these incredibly smart colleagues of ours who are creating this really rich data, and they're using multiple machine learning models in production to create it. Their specialism is data science, and their time is best spent improving the models, improving the data, and ultimately improving the value that we give to our customers. What we don't want to do is to dictate to them what the schema of that data should be. We don't want to be going back and forth to them over time, asking them to change little bits of the schema so it's more performant when we query it. So what we needed was a system that sits between us and the people that produce the data, and it gives us the power to actually control the schema ourselves. And that way we can do things like optimize our querying, like we can denormalize data and we can change the structure of it and the actual data types within our storage layer. So why would we build something like this in JavaScript? It doesn't sound like the sort of thing JavaScript engineers normally build. Well, it makes sense for us to do it for a couple of reasons. We have this pool of incredibly skilled, talented software engineers who are already consuming this data, and they're building the API and the analytics platform using it. We've already got this ecosystem of shared utility functions, of interfaces from TypeScript that we can use to actually scaffold something like this. And we're already using like most of the infrastructure we'd need, most of the kind of tools that we would need in other projects. Another really important part is that it's just a really good way for our engineers to upskill in other areas. So we have engineers who join Vortexa who they have some Node experience, some React experience, but if they're interested throughout their career, we can actually get them working on projects like this to pick up some data engineering skills and get exposed to different software architectures and methodologies. So we know what we want to build. How do we go about building it? In an ETL pipeline, we're going to be extracting data from a source or multiple sources. We're then going to transform it and maybe even enrich it. And finally, we're going to be loading it or syncing it into like a storage layer or multiple storage layers so that it can be consumed downstream. Now we can apply some additional steps like validating it. If you think about a system that is processing payment transactions, for example, if a payment comes in but it doesn't have any monetary value associated with it, it's not a valid record and it shouldn't end up in our storage layer down the line, because it could result in potentially bugs in our applications or just look really weird to our users. So we can apply validation during this process, and it can kind of raise issues and let us know that there are potentially issues upstream. So in front of you, we've got this basic implementation of an ETL process, and all of these different steps that I just mentioned are happening sequentially. But there's some things that we need to consider when we're looking at an implementation like this. So are we grabbing all of this data from this source? What if the data set is far too large for us to actually do that? And if the data set is too large, do we then need to grab just a subset of it? So if we've got a subset of the data, how much of it are we getting? And how are we tracking which subset that we've actually got? Are we just going to like mark it as fetched in a database? Or is it just a big file and we're literally reading lines out of that file and removing the ones that we grab? What happens if there's a failure after we've grabbed that data? It could now be marked as fetched in a database, or it could even worse have been just removed from a file, but it hasn't actually been processed and synced. Are we going to have to implement retry logic? Or even worse, is there a risk that we actually might lose this batch of data? These are the kind of sort of things that we need to think about, and this is the level of scrutiny that we want to apply when we're thinking about how to solve a problem and the systems that we need to build to solve it. So let's think about a different way of building the system and some of the design concerns and principles that we'd want to stick to. We can stop for questions if there are any now.
Yeah, absolutely. So we've had one come through from Anirudh who says, are the APIs written in Node.js or written in Java?
Our APIs that power our web applications are written in Node. So our team, application development team, I think I mentioned it's the biggest team in the company, and that's because we're just building a feature-rich web application and Node API, and they're both products. The API is a product to some customers, and the analytics app is, but the analytics app actually reads from the same API that our customers do, and it's all JavaScript.
Perfect. Another one come through from Nidish. You mentioned recoil.js for state management. Do you use Context API?
I don't think we directly use the Context API. Yeah, unless it's being used under the bonnet by some libraries that we're using, we're not directly using it.
Perfect. No other questions through for now, so feel free to carry on, and we can have another break for questions soon.
Cool. Let's keep going. So we've got this pattern, and we've kind of identified some issues with it. So we're coming up with a new system, and we want to think about the design concerns and kind of plan what we need to think about. So this pipeline that we're going to build, we want it to be modular. We want the responsibility for each process to be delegated to its own process. So we're going to have separate processes that ingest the data, separate ones that transform and validate it, and finally separate ones that load it into our storage. And this modularity, it will give us the ability to kind of iterate on specific parts of the pipeline and enhance the functionality or increase the performance of it. So should we choose, if we find we've got some serious issues ingesting data and we're reading Parquet files and the node libraries can't handle it for some reason, we could take that module out and replace it with a Rust one or a Python one, and it isn't going to affect the rest of the pipeline. We definitely need to build our services with robustness in mind. This pipeline is going to be processing absolutely critical data from upstream. Any disruption to it is going to result in us getting up at 2 in the morning and putting out fires, and it will have stale data in the UI and being exposed to our customers, and that's not what we want. So we want our services to be loosely coupled so that any failure is isolated and it doesn't interrupt the entire pipeline. I've got maintainability here, but really this isn't something special for this pipeline. Maintainability is something that we will have to think about with anything that we build. We're going to rely on our existing ecosystem of shared utilities and interfaces. We're going to ensure we implement the same level of automation and tooling that we rely on our other code bases. And we're going to document every part of this code base so that other engineers who are getting onboarded will kind of understand it a bit better. Probably the most important thing on this list is scalability. We want instances of each service to be added or removed and to respond to changes in demand. So we don't want our service to be kind of a bottleneck on the throughput from the upstream services, getting the data from them to our customers. We want to make sure that there are multiple instances of all of the critical services running so that they're more tolerant to faults and to any issues. We also want to deploy our system into some sort of process manager so that if for some weird circumstance that they were terminated, they're going to restart and we're going to have the number of instances that we want running. And finally, trackable with telemetry. We need to make sure that we have a comprehensive system of telemetry in place because this can alert us to potential issues. We want to look out for bugs in code, operational issues like network ones or database ones, and we want to know if there's any disruption to the flow of data through our system. So we can actually also track our throughput and visualize it, and that means over time we can see if there's any regressions. Okay, so we've kind of outlined our design concerns. These are the things that we're thinking about as we're trying to solve this problem. What does this pipeline actually look like? So here you can see we've split our processes up. It's no longer just one script where it's doing everything sequentially. And we're going to connect them together with some sort of a messaging system, and then we can scale them as necessary to perform what they need to do. In order to easily scale these processes, though, we need them to be stateless. So when I say stateless, what I mean is that each process can perform its task regardless of what the surrounding processes are doing. The transformer, for example, it will just receive a batch of data, transform it, and dispatch it. How it applies its transformation doesn't rely on any external state or any conditions that it needs to know about. A good kind of rule of thumb, one that I've definitely found helpful, and a thing to remember when you're building a stateless process for consuming messages, is that the stream of messages is potentially infinite. So your process shouldn't know about their IDs or what number they are in the overall data set. It should just literally take a batch of data, do what it needs to do to it, and then move on. When our processes are stateless like this, we can have as many of them running simultaneously as we want. If one of them was to terminate for some reason, it won't affect any of the others. And by building the ability to add more processes which are churning through this data, we can scale it up, and therefore we can maximize the throughput of the data in our system. And this is just showing kind of more modules being added. So let's look at a kind of real life schematic of the pipeline that we've built in JavaScript. To begin with, we have our upstream services. They're on the left-hand side, and they're creating this data and dumping it. We've coordinated with the other teams in the company so that they can produce this onto a messaging bus, and this is flowing into our transform processes. These transform processes are connected to a cache, which is being used to kind of enrich the data during the transformation process. And from there, we're actually then producing this enriched data onto another message bus, and this is going straight into our loading processes. And from here, it's going directly into our storage layer. Now, this schematic, you can hopefully see how we've stuck to the original design concerns I covered earlier. This is a very modular system. The services are loosely coupled to each other, and it's also scalable. So because we have multiple instances running, it helps with our robustness. Another design concern that we mentioned was telemetry and tracking errors. So there's an additional part to this pipeline called the logger or the controller. And this sits above all of the other processes, and it's kind of like the eye of Sauron. It sees everything. It's connected to the upstream processes and to the enriched data bus, and it's also connected to all of the storage layers. And what that means is the controller can literally track data from the first instance that we see it all the way through our process and into the storage layer. And to do this and to be able to be aware of if there's issues or if batches haven't come through, it needs to have some state. So it's actually unique in this process in that it's connected to a database, and it queries the database so that it can recognize if new batches are being ingested by it. But we've specifically designed the system so that the logger, the controller, the eye of Sauron, it sits above and it's kind of out of the way. So if anything goes wrong with it, it doesn't affect how this process actually runs. Before we move on, I'll show you a kind of simplified implementation where we actually talk about the tech involved. So this is exactly the same, but this time I've labeled what tech we're using in each step. So our message bus of choice is Kafka. Now, for those of you who haven't heard of Kafka or you don't know what it is, it's an open source stream processing platform which was originally built by LinkedIn, but now it's maintained by the Apache Foundation. It excels at providing low latency, high throughput system for handling data flow. Now in Kafka, data flows on what we call topics. And the best way to think about these is to think about a pipe with just data flowing through it. We can have as many processes producing data into that pipe as we want, and with as many consumers consuming the data as we want. The great thing about this is if any of our consumers crash, we can rest assured that they're not going to lose any data that's appearing while they're down, because it's going to stay in these Kafka pipes. And as soon as they're live again, up and running, they can start consuming the data from where they left off. So this kind of addresses the issue that we talked about originally, where what happens if your process crashed after it's fetched some data? And this is giving us a fault-tolerant way of ensuring data flows between our services, helps us mitigate the risk of losing data, which would be a catastrophic failure. For our cache, we're using Redis. Redis is an in-memory database or cache. It excels at providing extremely fast access to data, but one of its limitations is the fact that it has to hold everything in memory for speed, but it means that you can't have absolutely gigantic data sets in there unless you're paying for big infrastructure. It's the perfect system for us to use as part of this transformation and enrichment step, because we can quickly grab metadata out of it. Why might we need to do that? Well, imagine that the data we've got coming through our system it's like a denormalized record and it has like a vessel ID in it. During the enrichment process, we can actually grab all of the data about that vessel from the cache and then enrich the record, and we can put it into our storage layer for more performant querying. We're deploying all of our services to Kubernetes. We can rely on it to help us scale them based on memory and CPU thresholds. And we can also trust Kubernetes to spin up new instances of our processes if they get terminated. And this again goes back to our kind of robustness and trusting process managers. The ultimate destination for all of our data is Elasticsearch. For those of you who haven't used Elasticsearch, it's an incredibly performant search engine. It's capable of querying absolutely massive data sets and terrifyingly fast speeds. I've seen it handle queries that would genuinely make other databases just burst into flame. And lastly, we're using Postgres. It's just used by the controller to store logs about all the different data flows that are happening and when the data is getting into different processes and when it's leaving them, and just making sure that everything's going as we want it to do. And these are then just sent through to Slack as well, so that we're aware of them. I think now would be a good time to handle any questions if there are any.
Yeah, absolutely fine. So we've had one through from Cornelius, who says, what kind of process manager do you use at that scale? Does STH like PM2 fit your needs?
So we're relying on Kubernetes to, I kind of covered this, but we're relying on Kubernetes to ensure that all of our processes are running at the desired number of instances. So if processes are terminating, then it's going to spin up a new one to kind of match what we've said we want it to run.
Perfect. Yuri has said, how do you cope with security tokens?
So this pipeline isn't, well, first of all, we have an infrastructure team within Vortexa who are responsible for kind of maintaining all of our infrastructure. So our team can utilize clusters of like Elasticsearch clusters or Kafka clusters without having to worry about the configuration of them. So when it comes to security, obviously we deal with the security of our web application and our API, but for something like this, we don't need to worry about that. It's all happening on clusters and infrastructure, which is shielded from the open internet by our infrastructure team.
Perfect. Thank you very much.
And
so
yeah, that's definitely wouldn't be something that I'm hugely experienced in, but luckily for me, I've got colleagues who know their stuff.
perfect. Enric has asked, do you have any instances where order matters, or are all events independent?
We don't, and it's a really good question actually, because when you're consuming messages from something like Kafka, depending on how it's set up and the way you're producing and the way you're consuming, your order isn't always guaranteed. So in this particular instance, we don't have to worry about the order at all, which is a good thing. So we're just getting these batches of data and we're processing them and we're doing what we need to do with them. If order was a priority, then it would add a layer of complexity, but it is possible to kind of work with that.
Perfect. Anita has said, would you recommend any books or articles for designing and optimizing browser performance when interacting with APIs and optimizing websites?
Any books or articles? That's a really good question. Off the top of my head, I can't think of books or articles. There is a book that I've wanted to read for a while that a colleague recommended to me, and I think my team lead has read this book. Or is in the process of, and it's called Designing Data Intensive Applications. It's quite a big, thick book. I've heard that it's a really good kind of starting point. But aside from that, I think it's just a case of experience. The way that I've learned a lot of this stuff is from working at companies where it's set up and it's working well. Companies like Vortexa, joining teams of engineers who have built this and built it well, and learning from that. So yeah, sorry, I can't give a better answer to that.
Thank you very much. And one more question from Robert as well. He said, how does the data get into the upstream process?
So these upstream processes, I've kind of batched them all in just one thing, but really they could be a number of different things. So we could just have an S3 bucket that another team in the company is dumping data into, and that's being ingested and dumped onto a Kafka topic, which then flows into our pipeline. or it could be another team who's directly dumping that data onto a Kafka topic. But there's no one single source. This is, when I say upstream, what I mean is all of the other teams in Vortexa who are responsible for ingesting this data, applying a ton of different models to it, and ultimately creating our view of the seaborne oil world, essentially, which then comes to us so that we can transform the schema. So yeah, we use a lot of Kafka, but also a lot of processes that are dumping things into S3 buckets, which are then read by other processes.
Brilliant. One more quick question as well from Renee, who said, why did you choose Postgres for your database?
So a lot of the choices that we have here are based on already existing infrastructure. S3, I think there's probably not any company in the world that doesn't use it. Redis, for the reasons I kind of mentioned. Postgres, it's a database that we use extensively throughout the company anyway. So we're all familiar with the kind of the usage patterns of it, the API of it, and therefore it just made sense to use something that we know and already rely on and already have set up, as opposed to spinning up something like MongoDB, which we're not currently using, and having another piece of infrastructure to maintain and that sort of stuff.
Perfect. Okay, we've got no questions for now, so feel free to carry on and we can come back to any later.
Great. So the next thing I want to talk about is collecting telemetry and alerting on failures. And this was another big part of the design concerns that I mentioned earlier. The first thing that we have to understand when we're building these systems is that failure is inevitable. Nothing that I'm aware of has a long-term uptime of 100%. You're going to experience network failures. You're going to have database issues. You're going to have stuff like disk failures on some random machine in some warehouse somewhere with like an AWS logo on it. Perhaps the whole AWS or Azure region will actually go down at some point, and there's nothing that you can do about that. But what you can do is not be like this dog here and just sit and ignore the flames around you. We can make sure that we've got telemetry built into our system from day one, that it's not an afterthought that we've implemented when it's too late. Track your errors somewhere and be as thorough as possible in your code base when you're implementing this tracking. So in our processes, we're dealing with operational errors. These are the kind of ones I just talked about, and programmer errors. Programmer errors are slightly more different. They are the bugs that can be avoided in code. Examples of this, classic things: passing a string around when an array was expected, trying to read a property that is undefined. Everyone in this chat or in this Zoom has done that. That's a guarantee. Or trying to parse a string or something like that. Forgetting that a function is asynchronous and not awaiting the result. There's just too many examples to list. These are the sort of things that programmers introduce, and the way that we can mitigate them is to rely on tools to help us and automation. So things like TypeScript, they're going to prevent you from trying to parse a string or passing around a number or when an object was expected. We can also do things like implement static analysis on our code, things like linting. This should definitely be a part of your build process in CI, but also even locally in each developer's IDE with a shared config that's being pushed to the code base. Try and make sure that your team is conforming to the same formatting rules so that the code is more easy to understand and easier to review. And on that note, make sure you actually have a review process in place so that there's always a second pair of eyes looking at all the logic. You don't want to just be clicking that big button and merging into prod without a review. Try to keep your dependencies up to date, and therefore you can take advantage of bug fixes, performance improvements, etc. in your dependencies. But I would say probably the most important part of all of this, I should have brought that image up a bit earlier, sorry, is to know your language well. So let's look at an example of why you need to know your language well. When we're building a system like this, almost everything that we deal with is asynchronous. Now, if you want to avoid the callback hell, the dreaded callback hell, it makes sense to take advantage of promises, or even better, the async await, which is syntactic sugar for promises. The only issue with this is that async await actually makes asynchronous code look synchronous, which is misleading and kind of confusing, especially for less experienced engineers. A really common pitfall with this sort of code is what I've illustrated here. So we've got this processor function. It's calling another function, sync to database. And if we look at our sync to database function, let's just pretend it's trying to insert something into a database, but the database has gone down, so we get an error. This shouldn't be much of an issue. We've got a try catch block. We're catching the error. Everything should be good, right? Actually, no. Unfortunately, this will end up in a uncaught rejected promise error, which can actually cause your whole process to exit. The reason for this is that sync to database is an asynchronous function. So by the time it's executing, the code that has called it has already exited. So the try and the catch block doesn't exist anymore. This is probably a really good example, actually, of why just understanding your language can really help you to mitigate programmer error and avoid those kind of process terminations due to just small stuff like this. In this case, the solution to this problem is to make the parent function processor asynchronous and then just await sync to database, and then you have no issue. Your promise will get fulfilled with the error. Another really useful tool that we can rely on as part of our telemetry and error tracking are event codes. So you can see a very basic example here. These event codes don't have to be error codes. They just need to be planted throughout the code base in areas where events or errors occur. So for example, we've got this code there, TSFR-02. That's transformer number 2. This will get logged every time our transformer receives a raw batch from the raw topic, which is coming from upstream. And we can use these codes for a number of different reasons. They can be really helpful when we're debugging error logs, just either in like standard out or when we're looking in our telemetry user interface. They also give other developers kind of description of the cause or location of an error or event. But I would say probably the most useful case for these is that we can actually use them to delegate the responsibility of creating alerts to other software. So a really good example of this is the way we use it in our AWS infrastructure. Our processes are running in Kubernetes, which is hosted in AWS, and I'm sure many of you host in AWS too. And we can actually use CloudWatch to capture everything that gets printed to the console in all of our processes. So here in the screen, you can see a log from one of our processes, and this message and this code has been printed there. But what we can do is we can use these log groups to create metrics in CloudWatch. And to break it down kind of simply, I can say to CloudWatch, monitor my processes and just look for this code, transformer 2. If you find it, give it a value of 1. Then I can create an alarm that says, if you don't get at least the value of 10, which indicates 10 times that this message has been called in a threshold of, let's say, a minute, then it indicates that there's an issue with my flow of data. And if this happens, go into a state of alarm and start telling me about it, whether it's on Slack or email, or it doesn't really matter what it is. It could be text. Now, this isn't an advertisement for CloudWatch. It doesn't really matter what system you use. I'm sure there's many that do this. The point that I'm trying to make is we can reliably detect issues, even in systems that don't hold any state and therefore have no context about what they're processing. So in this example, our transformer doesn't really know if it's processed 1 batch or 100 batches. It doesn't know how many other instances of exact same code are processing batches as well. But what it does know is that every time it gets a batch, it needs to output this code to the console. And then we can actually rely on external services to monitor that and to tell us if the throughput has dropped or if it goes below an unacceptable or kind of alarming threshold. Before we move on, we can deal with some questions now.
Perfect. Just the one so far from Fabio, who says, what is the current Node.js version that the team is using?
I upgraded locally to 15 the other day. We try to stay very up to date with the dependencies, TypeScript versions, Node versions. Off the top of my head, I'm not sure what we're running in prod right now, but I would be surprised if it wasn't 14. But yeah, I can't remember off the top of my head, sorry. But we definitely try to take advantage of performance upgrades in new versions of software. We regularly will like go through our package JSON, update things as part of cleaning up debt, and make sure that we're running the latest TypeScript in Node. So it will definitely be one of the later versions.
Perfect. Another question from Nadish, who says, do you guys do paired programming?
We do, to an extent. So we have a very well-defined onboarding process, a program, which when new engineers join, we have a kind of structured Vortex Academy, so to speak, for them to go through, where they slowly will get exposed to more and more complex stuff. And as part of that process, they will be paired up with other engineers in the team who are experienced engineers who will work with them. We do still pair program together sometimes, but generally it's a case of you'll be pair programming with someone who's learning, or you'll be learning from someone who's pair programming with you, as opposed to just two developers tackling a problem at the same time.
Okay. Annie Rudd has asked another question as well, who says, how easy is it to get adjusted to TypeScript for a JavaScript developer?
I would say it's quite easy. From all the engineers in our team who have joined and didn't have any TypeScript experience, I would say they're a high proficiency within a matter of weeks. It definitely helps that they're being exposed to a full TypeScript code base. But the thing about TypeScript is, I believe anyway, once you start using it, you can never go back to JavaScript, because it makes things so much more robust. You will not have to deal with those annoying white screens of death in your React application because something's undefined. You always know what properties are available to you. And just by the number of times on a daily basis, TypeScript shows you an error where you're trying to do something wrong, it makes you shudder with the memories of writing applications in plain JavaScript where that wouldn't have happened and that would have gone into prod. So I think TypeScript is something that it's a reliable, it's a good tool to rely on. And if you're interested in it, it's definitely worth taking the time, a couple of weeks, to just kind of ease yourself into it and stick through the confusing part at the start where you're not sure what all the errors mean, because eventually they'll make sense and you'll never go back.
Brilliant. So a few more coming through here. So Robert says, do you use any loggers like Pinot or Log4j?
I've not heard of those ones, but as part of our telemetry system, we use Winston. It's probably the same as those ones, but Winston allows us to log our telemetry in multiple places at the same time. So we can send it to Azure Monitor, Application Insights, and also into the console as well. So I think that's the same thing.
Okay. Anita has asked, do you follow refactoring periodically, and how important is refactoring code in a team?
I think this is probably a better question for someone like my team lead, because he's the person who will prioritize when it's time to clean up debt and refactor things. But in my experience, I would say that we try to refactor things as we work on them. So there's not that many areas of our code base that are untouched for a long period of time. If we find something that's been untouched for a long time, we'll generally bring it up to date. But because things are always getting worked on, we will be constantly transitioning, and we're not scared to put something into prod when it's half finished. And what I mean by that is, let's say we decided to go from class-based React hooks to React components to functional ones. We wouldn't just spend a month converting the whole thing. We'd maybe do 5 files, merge them, do another 5, merge them. And that's what I mean by shipping things half done.
Okay, perfect. Another one through from John, who says, do you write any unit tests, or what tools or stack do you use for unit testing?
Yeah, we have quite a lot of tests, actually. We use Jest for unit tests, so things like utility functions, any transformation logic we'll be testing with input and expected outputs, that sort of stuff. We also have end-to-end tests, which will spin up the application. They will check different pages are loading, different pieces of functionality are working. We also rely on visual regression tests. So as part of our CI process, the app will be spun up and snapshots will be taken and they'll be compared to the master version. And if there's any visual regressions, like a button's broken or something like that, it will cause the test to fail, which will prevent us merging like a visual regression into prod. So yeah, extensive test coverage, all the kind of big names you'd expect, things like Puppeteer, Jest, something called Percy as well for the visual regression tests. But nothing that's probably no like weird obscure kind of libraries that you won't have heard of before.
Okay. Adish has asked another question saying, which tools do you guys use for monitoring your microservices?
So I've covered some of these really. We have Application Insights, which is part of the Azure cloud offering. We use it extensively for our telemetry. It allows us to just track events as they happen and also catch errors in our JavaScript code and our processes. But we also integrate with Slack to send notifications to Slack, and also things like CloudWatch. I kind of just talked about CloudWatch. We can use it in combination with our logs to give us alerts when things aren't in thresholds that we consider healthy. So this pipeline, for example, if we don't have anything flowing through it for a period of 10 minutes or even less, that's bad. It means something's wrong, and we want things like CloudWatch to catch that and alert us of it.
Perfect. All right, Blake, feel free to move on and we can get around to any of the questions later.
Great. So this is, funnily enough, it's the biggest slide in this whole presentation, and it's all about the things that I wish I'd known before I built this. So firstly, define your data schemas between the services as soon as possible. If you start developing services, but you're constantly changing the shape of the data that flows through it, you're going to have a bad time. This is especially important if you're not using TypeScript, because at least with TypeScript, it's going to force you to do this. But also with TypeScript, you need to make sure that you're actually sharing the same types and interfaces across all your services. I'd also make sure that I gain familiarity with all of the tools that I'm using. So it's super fun to just jump into something like Kafka, but there's a ton of complexity in the world of streaming, especially when you start concurrently streaming from multiple partitions, multiple topics at the same time. And this rule kind of applies to all of your infrastructure. If you don't know what the tools you're using are capable of, there's a good chance you can spend some time building some kind of weird replica functionality that you actually just could have had for free if you'd read the documentation and you understood the APIs of the tools that you're using. Really important one is mock your infrastructure locally. As JavaScript engineers, we need to kind of get rid of this idea that like Docker is some kind of backend tool that's mystical and magical and scary, and just we want to live in the browser the whole time. Using something like Docker, I can run this entire pipeline on my laptop in one command. So I can spin up a Kafka cluster, Zookeeper, the Kafka schema registry, an Elasticsearch cluster, Postgres, Redis, and something called LocalStack, which lets me simulate AWS on my local machine. So using tools like that are very important so you can develop locally without relying on real infrastructure. I wouldn't build something like this against prod data. For a start, it's unpredictable in how often you're actually receiving it, and it can make it harder to consume the same data twice, which is important when you're developing something. And also, you might just be completely overwhelmed by the sheer volume of it. Like, good luck trying to build a process and develop it and fix bugs when you've got 50,000 messages a second flowing through your pipes. So instead, mock all of your data locally. So build some like scripts that will dump fake data into your pipeline, and therefore you can do some cool stuff. Like you can control the volume of data. You can have one message flowing through or 10,000 batches of 100 messages. You're also able to make the data predictable, so you can confidently develop against the same data. But conversely, actually, you can also just break the data and see how it affects your pipeline, what breaks, and how it does break. From the start, a really important thing is to think about how are multiple developers going to work on this project at the same time. So if they've got two different environments, two different branches, and they've pushed them into the dev cluster, are they going to conflict with each other? With Kafka, for example, you have a consumer group ID, and it's what is used to know where you last were in your consumption. So if you've got two services or two processes with the same ID, they're going to be fighting against each other, and one will get 10 messages, the other will get the next 10, but neither of them will get the full picture. So something you can do to kind of separate everything by branch is use the branch name. This is normally part of the build process. You can access the branch name through your CI and pass it as an environmental variable. And you can use it to split everything in your pipeline: logs, cache key namespaces, even indices and Elasticsearch. I would say it's really important for you to test unexpected events. For example, what happens if my process dies midway through processing a batch of data? Get some tests written for this happening, and then you can sleep at night knowing that your processes aren't losing loads of data and destroying the insight you're giving your customers. And lastly, I think my team lead would agree with this one. Make sure that you configure your dev and your prod deployments in advance, so that when the big day comes, that this pipeline that you've been working on for ages is ready to go. You actually don't end up spending like 2 or 3 more days doing a configuration of deployments and messing around with environmental variables to sort it out. Sorry about that one. So what is the outcome of this project been for us? Well, our team now has full control over the schemas that we're putting into storage. And that means that we've been able to actually optimize some of our queries, and in certain cases, make them an order of magnitude faster. And there's a lot more work to be done in this kind of area. We've also actually got such a reliable telemetry system in place that we are detecting issues upstream before those services that are producing the data have actually thrown alerts themselves. And with some of the data sets that we're going to be adding this year, we've got really good possibilities and exciting possibilities to kind of bring the richest and most valuable data yet to our customers. So within our team, we've also got a great opportunity for our engineers to upskill and pick up some data engineering experience. And we don't have to hire a whole new bunch of people who work in another language, because we've done it in JavaScript. It's a language we already know, it's a language we use extensively, and we can maintain it and continue to build it and make it better. And obviously, it gives us just another cool thing that we can talk about at meetups. I think, yeah, the last kind of thing I'm going to show you is a screenshot from Azure Monitoring. And this is just showing some of the throughput through our system. So the spikes that you see here are caused by jobs that run in batches. So they dump a whole batch of data, and then they're silent, and then another batch. And then there's some services that are just dumping real-time updates. So this is showing at a granularity of 1 minute. So we can see that the throughput at points is 3 to 3.5 million messages per minute. This isn't by any means the limit of the pipeline that we've built. But we can go away and do some experimentation with the throughput, and maybe we'll save that for another presentation sometime. I think just to summarize everything, I would say that the stuff that I've talked about, this is the sort of problem that you can expect to solve at Vortexa. We're working with these large, comprehensive data sets and with real-time data. It's really incredibly fun, but it's also very challenging. We've got a tech blog. It's full of interesting articles, so please do check it out. The link is medium.com/Vortexa, but spelt like this. And it would be remiss of me not to mention hiring. We've been very lucky in lockdown. We've actually doubled the size of our team, and we're going to be doubling again this year. And we currently have the following positions open. We've got a senior lead full stack engineer, 2 junior or mid full stack engineers, and a senior engineer in automation and test. And the areas that we work in, we are ready to upskill people in all of these areas, regardless of their current experience. So if you're sick of making web banners, come push the boundaries with us at Vortexa. And with that, just thank you everyone for listening. Hopefully there'll be some more questions I can answer, but I hope it's been informative, and I hope some of you have been inspired to take JavaScript to the next level and build something cool with it.
Brilliant, thank you very much, Sean. We do have a few questions, if you don't mind sticking around just to answer those for them. So we've got one from Anita, who said, is it better importing third-party libraries for a functionality or building them from scratch?
That's a really good question. I would say you have to find a healthy balance between the two. If you want a component like, I don't know, a date picker, why would you reinvent the wheel? Like, Airbnb has an NPM package, which is a comprehensive date picker you can use. If it's good enough for their website, it's good enough for what we're doing. So yeah, find a balance. Don't bring in new libraries for no reason, because they always come at a cost in terms of the size of your bundle and stuff like that. But yeah, try and find a healthy balance.
Perfect. One from Mark as well, who says, do you use Docker Compose or Kubernetes locally?
So locally, I'm just using Docker Compose. I haven't found the need to spin up Kubernetes locally. Maybe we will in the future, but for now, just literally one command to run all our infrastructure locally is good enough.
Perfect. And one from Robert as well, who says, do you do Git flow with releases or trunk-based development?
We use we basically are merging to prod all the time, actually. So instead of having big releases which are being tagged like on a weekly or fortnightly basis, we're kind of iterating very quickly and constantly releasing. So yeah, hopefully that answers that question.
Brilliant. And one final question, which has come from Chris, a little bit out there. One last question, what's your favourite football team?
Sorry to disappoint, but I'm actually not the biggest football fan. I have bad memories from primary school where I was called Hacker Sean for taking people's shins off. So I've avoided it ever since. Although we do have a five-a-side football team in Vortexa, which is incredibly good fun, and I'm kind of starting to redeem myself there.
Amazing. Well, first of all, thank you very much, Sean, obviously for your presentation. I think you've done a really good job. Obviously, we've had some really nice comments in the chat as well, just saying how informative it's been and how good it's been. So that's obviously good to hear. Just a quick message from me as well that John's actually asked this in the Q&A section as well, that the presentations will be available on YouTube tomorrow. So anyone who wants to watch it, I'll do a LinkedIn post tomorrow, just sort of publishing that so everyone can see it. And if anyone is interested in hosting a presentation like Sean's done this evening, or you know someone who may want to do it, please do reach out and let us know. I'm more than happy to have you on board. But yeah, thank you very much, Sean. Really appreciate it.
Yeah, great. Yeah, thanks for having me. It's been my pleasure.
No problem at all. Have a great evening, everyone, and we'll catch up with you all soon.
Bye.
Take care. Bye-bye.